On the infinite two-dimensional plane, a tilling by regular hexagons is given, where initially, we consider only the hexagon's borders, while their interiors is left empty. Now, a game is played between two players, A and B, in the following way. At each round, first, player A chooses two adjacent hexagons and then fill their interiors. Then, player B chooses one hexagon whose interior is filled, and then remove this interior. Considering the previously mentioned rules, the players can keep playing the game indefinitely. However, if at any point, player A manages to fill the interiors of k consecutive hexagons where k is a positive integer, which is decided at the start of the game, between the players A and B, then player A wins, and the game is finished. This brings us to the main question in this challenge. We have the following main problem. Find the minimum value of the number k for which player A cannot win the game by using a finite number of turns. First, let us show an example of the number k for which player A cannot win the game. For this, let us emphasize in a periodic way, in each column, the boundary of the hexagons in each sequence of 3. This is done in such a way that every two consecutive columns, which are not adjacent, have the same pattern. Then the columns that are left are emphasized in the same way, but by using a translation. With this pattern, all player B has to do is to make sure that at each turn, if the interior of one of the emphasized hexagons is filled, then this interior is moved out. This implies that at the beginning of each round, player A can fill the interior of at most one emphasized hexagons. Hence, at no point, player A can fill the interiors of 6 consecutive hexagons, since then 2 emphasized hexagons must be filled. In conclusion, the minimum number k that we are seeking is smaller or equal to 6. We will now show, in case where k is equal to 5, that player A can use a strategy that will guarantee his victory after a finite number of turns. This answers the main question in this challenge. Let us now describe explicitly the method that player A can use in order to guarantee his victory. At the first turn, player A fills 2 hexagons and then player B moves one of them. Hence, at the next turn, player A can fill another 2 hexagons, so that, in the end of this turn, we will have an equilateral triangle of hexagons which are filled. After another filled hexagon is moved out, we have 2 filled adjacent hexagons at some column. Then, player A fills another 2 hexagons on this column, such that exactly 2 empty hexagons separate the 2 pairs of hexagons which are filled. Let us denote by X and Y the 2 inner filled hexagons in this column. Observe that from this point, player B must remove either the hexagons X or Y, since otherwise, in the next turn, player A can fill 5 consecutive hexagons and win the game. After one of the hexagons X or Y are moved out, player A can fill this hexagon again, and also fill another hexagon which is adjacent to it. Hence, since player B will always remove either the hexagons X or Y. If this process continues, then after a finite number of turns, either the hexagons X or Y will be completely surrounded by hexagons which are filled. Let us assume, without loss of generality, that this is the hexagon X. Then, at the next turn, player B must remove the hexagon X, or else player A will win. Let us look now at the two empty hexagons which are emphasized. After player A chooses to fill them, we have the following two consecutive sequences of 5 hexagons which can be filled at the next turn. Since these sequences are disjoint, it follows that no matter which move player B will perform, player A can guarantee that in the next turn, at least one of these sequences will be filled. Hence, after this move player A will win the game. This proves our assertion, and thus our proof is finally complete.